In this segment, I'm going to continue our discussion of fluid properties, in particular properties related to density and also some discussion of normal stresses, which are pressure. In the handbook, we have several definitions which are related to fluid density. The first one, density, which we normally denote by the Greek symbol or the Greek letter rho, is the mass per unit volume, defined as delta m over delta v, where delta m is the mass of the fluid contained in an infinitesimally small volume, delta v. A close related property is the specific weight, which we normally denote by the Greek letter gamma, where gamma is the weight per unit volume, delta w over delta v. And a final related property is the specific gravity, which doesn't have a specific symbol associated with it. We usually express it as Sg, and the specific gravity is defined as the weight of the fluid divided by the specific weight of water, or the density of the fluid divided by the density of water, where the properties of water are taken under typical standard conditions of temperature and pressure. So these definitions, rho, the density of the fluid, has dimensions of mass per unit volume, for example, kilograms per cubic meter. Gamma, the specific weight, is a weight per unit volume. Weight is a force, so it has predominant fundamental dimensions of force per unit volume, for example, newtons per cubic meter or pound force per cubic foot. The specific gravity is a pure ratio. It's a pure number. It doesn't have any dimensions or any units. There is a simple relationship between the specific weight and the specific gravity, and that relationship is gamma, the specific weight, is equal to the density rho multiplied by g, the acceleration due to gravity. And one other piece of terminology is that if the density is constant, in other words, the density of the fluid doesn't change as we change the pressure, then we call that fluid an incompressible fluid, or constant density. And generally for this course, we will assume that all of the fluids are incompressible. In other words, the density is constant. And this will even apply to air. Particular values that we'll be encountering very often is the density of water, rho w, is approximately 1,000 kilograms per cubic meter, or 62.4 pounds mass per cubic foot. The specific weight of water under standard conditions is either 9,810 newtons per cubic meter or 62.4 pounds force per cubic foot. Now let's do some examples, and the first one is that we're given that gasoline has a density of 680 kilograms per cubic meter. The specific weight is most nearly which of these alternatives? And usually at this point I will pause briefly so you can try these examples and then check to see if you got the right answer. So here's the solution. Our definition of specific weight is gamma is equal to rho times g. In this case, we're given that rho is equal to 680 kilograms per cubic meter. G is 9.81 meters per second squared. Therefore, the specific weight is 6,671 newtons per cubic meter, and the closest answer is B. Similar problem. Gasoline has a density of 680 kilograms per cubic meter. The specific gravity is most nearly which of these? So again, the solution just follows from the density. The definition of specific gravity is equal to rho over rho w, or equivalently gamma over gamma w. In this case, we're given the density is 680 kilograms per cubic meter. So the specific gravity is 680 divided by 1,000, taking the density of water as 1,000 kilograms per cubic meter, and the answer is 0.68. So the answer is D, 0.68. Now, stress is force per unit area, and it's defined in this way: the limit as the area tends to 0 of delta F over delta A, where delta F is the force acting. And in the FE manual, they decompose the stresses into the normal and tangential component, where the normal component, the magnitude of the normal component, is the pressure, or the normal stress. So pressure is normal force per unit area, in other words, F over A, force per area. So therefore it will have fundamental dimensions of force over area, which would be either newtons per square meter typically, or pounds force per square inch in the system of units. We have some special units here. A newton per square meter is written as PA, where PA is a Pascal. So Pascal is the metric unit for pressure, newton per square meter, and pound force per square inch we usually abbreviate as PSI, pounds per square inch. The Pascal, however, is a very small unit. For example, the conversion, 1 pound per square inch is almost 7,000 pascals. So because the Pascal is a small unit, more commonly we will be using kilopascals, which is 1,000 pascals. For example, typical tire pressure, say, of 30 pounds per square inch is approximately 207 kilopascals. Now, another very important convention in expressing pressure is whether we express it as a gauge or an absolute pressure. The difference between these is that the gauge pressure is relative to atmospheric pressure, but the absolute pressure is relative to absolute zero. So if we're expressing our pressure as a gauge pressure, we would denote that by PSIG for gauge pressure. However, almost always we're only interested in gauge pressures. In other words, pressures relative to atmospheric, so we don't normally need to add on the G at the end there. So if we simply write PSI or KPSA, it's implicit that what we're referring to there is a gauge pressure. In other words, a pressure relative to atmospheric. If it's an absolute pressure, we have to put an A on the end here, or an absolute after KPA to denote that we're talking about an absolute pressure. And that is essential in that case to distinguish it from a gauge pressure. So normally, if we just say PSI, then we were referring to a gauge pressure. Standard atmospheric pressure that we'll use fairly often is approximately 101.3 kilopascals absolute, or 29.921 inches of mercury, or 14.7 psia will be typical values that we'll use. And atmospheric pressure, by definition, is always, of course, 0 psi gauge or 0 kilopascals gauge, by definition. And the relationship between the two is that the absolute pressure is equal to the atmospheric pressure plus the gauge pressure. We also have another convention, the vacuum pressure, and vacuum pressures are useful if the pressure is below atmospheric. In other words, it's a negative gauge pressure. And the vacuum pressure is simply the negative pressure expressed as a positive number. So in that case, we would write it as PSI vac or KPA vac to denote that we're referring to a vacuum pressure. So let's do some examples on that. We're given that the liquid in a closed tank has a pressure of 50 kPa, kilopascals, and that implies that it's a gauge pressure because it's not specified. If atmospheric pressure is 101 kilopascals absolute, the pressure is most nearly which of these alternatives? So here's the solution. Simple definition. Absolute pressure is equal to atmospheric pressure plus gauge pressure. In this case, the atmospheric pressure is 101, the gauge pressure is 50, so the answer is the pressure is 151 kilopascals absolute, and the answer is C. Similarly, liquid in a closed tank has a pressure of minus 20 kilopascals. Again, that's an a gauge pressure. In other words, it's below atmospheric pressure. If atmospheric pressure is 101 kilopascals absolute, the pressure is most nearly which of these alternatives. So the first one is obviously not correct because a vacuum pressure is always a positive number. It can never be a negative number. So here's the solution. The vacuum pressure is equal to atmospheric pressure minus absolute pressure is equal to, in this case, 121 minus 101 minus 20, and the answer is 20 kilopascals vac. So the answer is B. It's just the gauge pressure expressed as a positive number.